Let's move forward to the next talk. Now I introduce Professor Mustapha Jouiad from University Picardie, Jules, Verne in France. Professor Mustapha has a master's degree in solid-state physics and physics of particles from the University Paul Sabatier in Toulouse, France. And he has a PhD in material science. He has experience working in the material science program at Masdar Institute of Science and Technology, as well in the University of Illinois, Urbana-Champaign, King Abdullah University of Science and Technology, national laboratories in France, like CNRS, and the Lawrence Livermore National Laboratory. So welcome, Professor Mustapha. The floor is yours.
First of all, I'd like to thank Dr. Boucharka for this invitation, as well as the organizing committee. And I'd like to thank the chair for this nice introduction. Well, today, what I'm gonna do is to share with you some of our work regarding the nanomaterial engineering. And I will explain our general approach and provide you with few examples what we have done so far for a summary for about 6 or 7 years. So the main idea behind this is to try to tune the material properties, especially nanomaterials properties, for targeted application. So before going to there, I'd like to give you the big picture of nanotechnology, where the nanomaterials stand. And this chart, for example, shows that the nanotechnology is mostly dominated by nanomaterials and electronics compound. And in this table, and I showed this at the global market that is growing, especially the nanomaterials is getting more interest. And the market in the 2021, we reached $3 billion, which actually very high percentage in terms of investment in for nanotechnology, which actually more concern nanoparticles. So this definitely means that nanomaterials are getting more interest and in variety domain of industrial sectors. So let me show very quickly how it's when I talk about nanomaterials, what I especially focus on. So basically the first step is what is going on in the laboratory. So here the nanomaterials types. So basically it concerns the development of TRL below 2, which there is the first development of nanomaterials. Then we go to the intermediate development, TRL above 3, when we actually integrate these nanoparticles in special composite device for different applications, for sensing, solar cells, or for example, for memory or for coated materials and so on. So this is the second step that goes also in the laboratory, and this is basically our, when we bid for project in European project or industrial project, this is what we propose to them. So the next step is actually the nano-enabled product. When you have the finished product where the device is implemented and functional. And the last step is go to the big logistics regarding the implementation of these materials and also the MBC, the commercialization. So what is the challenge here? So the third challenge is to deal with nano particles or nanomaterials, which actually very difficult in terms of fabrication, modeling, and inspection. All the tools should fulfill these steps. So in terms of fabrication, modeling, the physics change, and let's see, physics is, we are at very low scale, and the inspection, the tools of inspection are very tedious and difficult to overcome. So the basic, what we do here in the research in our approach is to try to combine these three approaches, fabrication, model, and inspection, or characterization, to give the material insight and also to actually implement this material for specific application. So first of all, one of the questions that we were asking ourselves is why we do actually material engineering. So first of all, I'd like just to point out here that functional materials are very well desired, because now with the growing demand of energy, there is more focus not in one property of materials, but materials presenting different functionalities that can fulfill many requirements in terms of energy. And also, this is the first challenge in terms of demand of industry. And the second interesting point is research point of view. So nanomaterial design, fabrication, characterization for targeted application is very complicated topic, and it's very challenging to tackle it in nanotechnology. So to answer to the question, why study the engineering of material is, first of all, to comprehend at least the limit of nanomaterials, how far we can go to get insight to the properties of nanomaterials, and also their evolution in surface. So these nanomaterials, they have a lot of boundaries. They are small enough that the surrounding environment is much more important than materials itself. And second thing is to lead to functionalize these materials, to obtain much broader properties than specific one, when we know that we can shape the materials to obtain the specific property. So, and also another thing is by decreasing the size of the material, we grow the surface area and surface of contact, and we may also decrease the cost, and we increase the while we increase the performance. So I will give you some examples. So one of the examples, so this is one of the work that was featured as hot paper in PCC. So we implemented composite material in order to produce clean energy as hydrogen by water splitting technique. This water splitting technique is very well known. It's even natural process, and it involves semiconductor, basically titanium dioxide, which actually, when it is in contact with water, with impinging, for example, solar light, they may decouple the atomic bonds in water and producing in conductive band hydrogen and the in valence band the oxygen. But this phenomena is not continuous, and also is very low in terms of efficiency. And titania is another issue with titania. It has high band gap. It means that it has more response in UV region, which represent less than 5% of the total solar energy spectrum. So the idea is to add another noble material. For instance, here is gold, for a different reason. First reason is to increase the absorption of titanium oxide in full solar spectrum. So at least visible light, which actually represent 55% of the solar energy. This is one good thing if we add the gold. And another thing, by creating interface dielectric and metal, we create what we call plasmonic effects, when the electrons of metals can be actually excited to reach the conductive band of titanium. And this will help have more electrons in conductive band of titanium oxide and increasing efficiency of water splitting. So we did this in first in neat material, it's a film, and then we made a composite device. Sorry, we made a device that has a specific shape to increase first the surface area, because we decrease the size. Then it has a specific shape to actually to attract water molecules. So the next, the process is just to show you technically how it works. So basically, when we create here in the right, this micrograph showing titania and also gold. When you have here the interface between this dielectric and this metal, we create this interface when we actually excite the electron from in the gold. They are excited. This is what we call them hot electron, and they are able to jump and to go to conductive band of above Fermi level to reach the conductive band in titanium. And this phenomena is known as LCPR, so localized surface plasma resonance. So the whole process that we have done is to make this device and check if we are really, check first the performance of the device, then to explain why the performance is good due to LCPR. So what we did to understand first how it goes when we actually prepare the first neat material. So what we did here is the first composite I showed you many films, and the top of it you have a gold, and we did different ultra rapid annealing. So annealings to anneal only the top surface without touching the substrate. And we were able to actually control the assembly of the gold nanoparticles. And here to show that by doing this just rapid annealing, we were able to increase the contact between titanium oxide while keeping the percentage of gold enough to make this interface very high. So as we have nanoparticles, we have high contact in terms of with titanium, better than having a film. So what we did also, we manipulated the orientation in our film by doing a specific crystallization. So here I can show you before we do the manipulation, we have material with different grains. Each color means different orientation. And this has happened if we do regular annealing, but when we do rapid annealing under high pressure, we are able to reorient all the grains along one facet orientation, which are actually known to be highly efficient in terms of absorption of visible light. So first we manipulate size, manipulate orientation, and now we can check the absorption. So to check the absorption, I can show you here the evolution of absorption based on the annealing, and you can see in the gray and in the red line, which actually the film without any annealing, and the green and the blue with annealing, you have 5% increase in terms of absorption in the visible region. So this is only for the film. And also what we create, so to explain this, so we did some PL, photoluminescence, and for titania, and also for annealed composite. And you can see for the annealed, which the red curve, we have very sharp absorption in UV, which is actually normal because we have titania, but what we created SPR phenomena in the visible region. This is the origin of why we have the enhancement of absorption in the visible region. So now we go through our device. This is the device we made, and this is the top view and the side view. They are like cup shape. So with the capillary, they can attract more water, and also it's double interest, these cups, because first they can trap water and they can trap also the light, because the light will be scattered inside that cannot be taken off from these shapes. So this is how it looks like the device at 3D, and you can see most of the gold is on the top and the middle of the cups, and you have the stand, and this is reconstructed 3D using slice and view technique by FIB-SEM. So now to test our device, here we put very simple way to test it. What we did, we just made at 0 volt, and we tried to put light on and light off and to see. So of course, and we did it at different wavelength. So, and we have the maximum response in the visible range. So in the visible range, we have the maximum response and we have the current occurring when we shine our device with the visible light. And this is interesting because we moved it from UV to visible light. So similarly, and this device has double interest because even with heat, it will render some current. So we just put soldering tip next to the device and we measure some current with the low voltage on the edges in the connected of this device. So with sunlight heating and sunlight also the absorption, both of them will create some hot electron that we are looking for to actually inject in the conductive wire of titanium. So now we will check if there is this hot electron existing really. So to do that, we cut very thin lamella, and then we excite we took the response of the device with and without excitation of electrons. And we can see that we have in red extra peak coming from plasmon. Then if we take the image from this peak, and this is how it looks like, and we can see the antenna, we can see here antenna in these edges here, and this is occurring at visible light. This is very interesting. So now we are sure that we have created some electron in the edges, which actually in the interface between titanium and the gold. Sorry. So next is to show, this is a summary of it. So we have a presence of LCPR, and it is in visible region, and it is coherent with the photoresponse we just showed you. And this is indication that we can create hot electron that can be injected in the conductive band of titanium. So this is another deeper insight about this LCPR. And what we did here, it's high resolution microscopy combined with another technique, elemental technique called Energy Electron Loss Spectroscopy. This is show that we have this excitement everywhere in our new shape that we call it hook, fish hook-like shape. And we have another shape with actually asymmetric rod. I want to, for the people who are not familiar with plasmonic are very sensitive to the size of the particle and also the shape. And here we introduce it for the first time, this kind of shape in the literature. Basically, all existing study is about regular size, like regular shapes, like spheres, triangle, rectangles, stars, and so on. And this is, we introduced this one. It has very high interest because it shows the excitation in all energy windows. It means that we can travel from UV to visible light, and we can still create these hot electrons in this star. It's better than what you see down for nanoparticles here, that we have a very broad excitation. So simulation, FDTD simulation rendered exactly the same response as we obtained in experiments. So we draw this shape in our simulation, and we did and we obtained exactly the same excitation at all energy windows. And this is very interesting. It means that our shape can create the hot electron that can be which actually the origin of the high efficiency of our water splitting device. It's reaching 88%. So the second example is about I finished the first example. I give you the second one regarding the silicon germanium. So this is highly desired material in PV, so photovoltaics. So what we did, we selected very easy technique called PCVD, but enhanced plasma CVD. So this is very straightforward techniques that help to render or to fabricate very easily silicon germanium. But everything is done after the fabrication. concerning the right heat treatment that we have to apply to increase the crystallinity for silicon germanium and also to lead to different composition. The idea here in this work is to try to engineer the band gap of this material. If we are able to engineer to lead to different composition of silicon germanium, we will obtain different band gap, and this will help definitely to have different layers of silicon germanium with different band gap. So what we did, this is as fabricated silicon germanium, and then we did the heat treatment, and we used, so when you fabricate first this silicon germanium, because silicon and germanium has very huge mismatch. So what we do, we start with the seed of silicon, then we go slowly, gradually, until we obtain the silicon germanium. And when we do heat treatment, we release the stress inside this composite. So using this stress release, we were able to lead to different compositions. So even we were able to reorient our grains. So they can be used, for example, like waveguide. We didn't try that, but this is one of the possible application of this composite. So what we did, basically, we did different heat treatment. It's rapid thermal annealing, which actually consists only for annealing the top film without damaging the substrate. And we did at different time and different temperature, and this is a lead at different stress. And stress by using Tseng model, we were able to obtain the stress release and also the composition of silicon germanium. And you have the content down here. This is Raman shift, and we did the same thing with XRD, and we obtained exactly the same composition here. You have the composition percentage of germanium in our silicon germanium compound. And they are always similar, and this is led to us to different composition, and we measured the band gap for each composition, and we were able to do, by starting from as deposited and doing different heat treatment with the relaxation, we can obtain band gap as different as from go to 0.6 to 1.09, which actually will cover a very large known band gap of silicon germanium. This is very interesting. So the third example is about layered materials. Yesterday, our colleague talked about, so actually layered material are material 1 atomic thick. So they stand in only, they have covalent band in the plane, and out of plane only van der Waals actually forces. So yesterday we had very nice talk about boron nitride, exactly hexagonal boron nitride. Today I will talk more about the decalcogenide. So here all the kind of, so 1 atomic thick material, which actually 2D materials can be graphene, can be semi-metal insulator, superconducting semi-metal, or semiconductor. So I'm interested more in semiconductor 1, MS2. Why? Because for graphene, it's gapless, so we cannot tune the band gap. We cannot use the properties of semiconductor, and also prone to contamination. So, for example, for sensing, graphene is not reproducible as it is sensitive to environment. It's not the case for the MS2, which has first band gap, and also it's relatively more stable compared to sensitive material. So if it is stable, we can produce it. So before getting to that, I will show you the quickly application of MS2. So it depends on its form. If it's monolayer or multi-layer, it can be used as gas sensor and so on. I let you see the all possibilities. Can even be used in DNA sequencer, hydrogen evolving cathodes, also lithium-ion batteries, and photodetectors and so on. So for our case, we developed a new technique to make this MS2 straightforward, easily. So just by using CVD with sulfurization, And you can see here in this tube furnace, for example, I just put schematic of what's going on. We just put the sulfur as first precursor and molybdenum oxide as second one. And then we can choose any kind of substrate, and we are able to produce our MS2 materials. So basically, we obtain different, morphologies, and we all are actually documented. I will today talk only about the needle-like shape, the MS2 that they are aligned vertically to the substrate. So this one are very interesting because this I will show you here, for example, TEM. You have silicon atoms, you have Si2 as a sacrificial layer, and you have the MS2. So what we obtain first, the first amazing result is to obtain for the guy are not familiar with MS2. MS2 it shows PL only when it is monolayer, only one atom thick, 2D material. Here with our needle-like shape, even if it is multi-layer, we're able to observe the PL, which actually interesting. We can compete with very complicated MS2 monolayer by just doing this straightforward technique. As we saw it's interesting, we tested for field emission source, and we can show you here this month. Our MS2 were able to show exactly the same behavior as a field emission gun. So it can be used, for example, for microscope guns, and it uses only very, very low voltage, can even be used as cold emission gun. So we used MS2 also for the sensing, and here I show you some examples on the MS2 needle-like shape, sensing sensitivity for NO2 and also for ammonia. And we can see that we have very interesting results that the sensitivity, it was part per billion, which is actually very, very competitive with existing sensing system. So another thing, so we wanted to check the sensitivity of our sensor when in the presence of moisture. So most of the sensing materials are very, it's very complicated to do sensing in the moisture environment. So it is good to understand the behavior of our sensor before rendering the result that we obtained for different gases. So here we are able to draw the behavior of our sensing versus moisture. So basically, our MS2 shows high gas and moisture sensitivity, and very competitive with mono-layer MS2. So the fourth example is concerning basically the nano actuator fabrication. To do that, we used a dual beam system consisting of electron column and the IM column, which is known under the name focused IM beam, FIB-SEM. So this system can do imaging, can do milling, and can do also deposition. So we use this third properties of focused IM beam to fabricate actuators. So here in this image, we can show you that we produce nanopillar of PT carbon composite, and just using electron excitation, we're able to bend them. So we were able to measure the bending energy, to measure the excitation energy, and the bending angle. So we control the whole process of the bending of the system, and we understand the mechanism of the bending. So by doing that, we were able to make very, very nice nano futures. I can show you here, for example, we can do nano cages, so and that we can excite, and just by thermal, and we were able to do some manipulation at nanoscale. So in the end of the day, if we are able to make for 1 pillar, 4 pillar, we can do whatever shape it is possible. So we're able to make, for example, in B, nano switches. So this is the switches that can be used at nanoscale, nano cage, nano grabber. We can grab things at very, very, very low actually dimension. This is very interesting. So as summary, I came to my conclusion. So I hope that I was able to show you that novel water splitting device was fabricated using LCPR material, which seems to extend the optical absorption of the titanium to visible light. This is one of the first good interesting thing about this device. Second thing is that devices show photoresponse in the full solar spectrum. And also its performance can be enhanced just by thermal annealing. This is very interesting. So it means under the sun, the heat will take also advantage of this device. The second one example, I showed you how we can engineer the band gap in silicon germanium. So we did just straightforward fabrication of silicon germanium, but with the specific annealing, we were able to engineer band gap. So then I showed you how we did fast cell fabrication of vertically aligned MS2, that they have very specific orientation of their needle. They are like needle-like shape, and they have very good property as for monolayer. So they are also high sensitive to some gases and moisture. So in the last example, I showed you that we were able to make in situ electron deposition and to fabricate very small tools, nano tools that can maneuver or can actually switch some electronics at very low scale. This actuator can be used in very broad application in optoelectronics, electronics, and so on. Before finishing, I'd like to thank the people. Without them, this work cannot be achieved. So my team, my collaborators from France, MIT, and Mazda, and also the sponsor who paid for this work. And I thank you all. Thank you very much.
Thank you, Professor Mustapha. Very nice talk. Now the floor is open for questions. I have a question regarding the development and the application you have proposed. These are very, very interesting. This work, as you have mentioned, present some challenges regarding the laboratory work and this step towards let's say the massive application of this technology. From your point of view, what do you think is the bottleneck of this technology to move forward, to give the next step in the wide use of nanomaterials and nanotechnology?
So actually, it's this is what I explained here. So this is what we have done in laboratory, and so all of these nanomaterials are implemented in the second step. Right? This I'm talking about terms of the laboratory. So so the next step for the nanomaterial is to be implemented in device. And for one of the examples, the device that we showed, that device is straightforward usable for water splitting. And we have to know that, I will just give example, if we go from bulk material to nanomaterial, we increase the contact with millions. So it means that because the surface area per kilogram, per gram is huge in nanomaterials, and this will help. It's what is, for example, can happen with bulk material, which will be increased, enhanced, tremendously. And this is one of the interests of nanomaterials.
Okay, thank you very much.